In this lecture I would like to talk about Stokes' theorem, which is also known as the curl theorem. Similarly to the case of the divergence theorem, in this case there is a transformation, but it is not a transformation between surface integrals and volume integrals. In this case, the theorem tells us that it is possible to transform a line integral into a surface integral. Let's consider a curve, a general curve in 3D space. So this curve can either lie on a plane, but it can also in general lie in space, so it may not lie on a plane. This curve I will call gamma. It will be traveled in anti-clockwise direction, so it's oriented in anti-clockwise direction. The theorem tells us that if we take any surface which has as a boundary this curve, and I will draw this sort of surface, which is an open surface, so this is not a closed surface. The curve has to be closed, but the surface, which I will call sigma, is open, because from here we can enter the surface from downside. And the theorem tells us that the line integral over gamma of a vector field f dot dl, you can also put it in the form tau times dl, where tau is the tangent vector along gamma. This is equal to the integral over the surface sigma of curl of f, which is the cross product between the del operator, which is the gradient, and the vector f dot n, which is the normal to the surface, times ds, which is the element of the surface. So this theorem is very useful. It's pretty much used all around physics. We will try to prove this theorem in this lecture, so let's try to work it out. We will consider at first an infinitesimal surface, actually an infinitesimal curve. What does it mean to consider an infinitesimal curve? I will take a curve lying on the xy plane, so this is direction x, this is direction y. This curve is a closed curve, as you can see, and this small element has length dx, whereas this small element has length dy. Essentially, what we have to do is to consider this integral and try to compute it for this very small curve, which is almost down to a point, because this point here is the point xy. If you want, there can be a z as well, but we are on the xy plane, so z is 0, I will not consider z. With this point here, for instance, is x plus dx, y and z. This point, for instance, is x, y plus dy, z, and so on and so forth. When we have to consider this integral right here, we have to do a dot product between f, which has components fx, fy, fz, and dl. dl has components dx, dy, dz. When we do the dot product over this line, for instance, we only have a contribution given by fx, because fx is moving just parallel to this line, whereas fy and fz are perpendicular to this line, so we get zero contribution from the dot product. So in here we get from this contribution fx, and we can calculate fx where we want. It's almost constant because this line is infinitesimally small, so we can calculate fx at this point, fx of x, y, z, times the length of this element, which is dx. And then we have this contribution, which is given by plus. We have fy here, right? This is fy, and fy is moving upwards. We take fy to be positive if it goes along y, the direction of y, because the vector f can be written in the form fx times I plus fy times j plus fz times k. So the jth component is positive if it moves along j. So we have fy. Where do we compute it? We can compute it at this point or any point on this line. I will compute it at this point. The choice is up to you because this line is very small. I will compute it at this point, so it will be fy of x plus dx yz times dy, because in this case the dot product is just 1 between j and the direction of this line here. Let's move on to this one. In this one we have fx, which is moving in this direction, remember it, because fx goes along I. So in this case we get a minus sign given by the fact that the two directions are opposite each other, minus fx. Where do we compute fx? We can compute it at this point, for instance, or at this point, but I will compute it at this point. So it is fx of x, y plus dy, z, times the length of this guy here, which is dx. And then we have plus this contribution, which is given just by fy, but in this case this direction is opposite this one, so we get a minus sign. So this is a minus fy computed at one of these points. I will compute it at this point, so it's fy x y z times dy, because it's the length of this element. So what is this thing? This thing is just this line integral. It's the entire calculation because we are integrating over infinitesimally small elements. So this is the result of the integration. If we take this part and this part together and this part and this part, I can rewrite it like this. So it's fy of x plus dx yz minus fy of x yz times dy, and let me divide by dx and multiply by dx, and then we have plus, I can extract a minus sign from this one and this one, minus fx of x y plus dy z minus this guy minus fx of x y z times dx. Let me divide by dy and multiply by dy, and this is equal to, this is the derivative of f with respect to x calculated at the point x, y, z. So we have df y over dx at the point x, y, z minus dfx over dy times dx dy. And this dx dy is just this surface right here. It's the surface ds enclosed by that curve. This is the result of this calculation. And if you take a look at this part right here, what is this? If I take the determinant of this expression, d over dy, d over dz, fx, fy, fz, if I take the kth component, this determinant gives me a vector, right? But if I take the kth component, I have I times something plus j times something plus k times k multiplies d f of y over dx minus dfx over dy. So this is the kth component of this determinant, but this determinant represents the cross product between the nabla operator or the del operator, which is none other than the gradient. So we have a del cross f, and we take the kth component of this, so we multiply this by k with a dot product. So if we want to take the kth component, we multiply this vector by k, the kth component. Okay, so all in all, this expression can also be written in this form. This is the cross product between the nabla operator and f dot k times dx dy, but k is just the normal to the surface dx dy, so we can rewrite it as nds. So as you can see in this case, if the surface is this one, we get the theorem, because we obtained that this integral for this very small curve is equal to this expression, because we have del cross f dot nds, where the surface is just the part which is inside this curve. It's the area of a rectangle, this very small rectangle. In general, I can do something very similar for the other planes, the yz plane or the xz plane. I will obtain something very similar to this. The result will be the same. I will have some projection of the curl of f on the surface, along the normal to the surface in particular. When we consider an entire curve which is not infinitesimally small, I will have all these very small contributions. For instance, if I consider these small contributions, what happens? Let me just consider two of these very small curves close together, okay? If I consider those two curves close together, I have this one. So take a look at what happens at the boundary here between the two curves. One of them I will move downwards, and one of them I will just move upwards. But these two contributions cancel each other. They give zero altogether. So when I consider the curves inside, I will not get any contribution. So the only contribution I will get will be given by the parts that lie along the line, okay, along this line here. So all in all, I can consider any kind of surface, even surfaces that come out of the plane. Even in here, I could have considered which came out of this plane. It doesn't really matter. The theorem is the same. So the result is just this one right here. It's this theorem. I explained it without any accurate rigor, but we will now apply the theorem to the case that I considered the last time. We will calculate, in particular, the integral along a circumference, okay, with radius r, and we have a field of the kind f minus y and x. We already computed the result given by the integral of f dot dl, which was given by 2 pi r squared, but we will compute it in the next lecture by applying Stokes' theorem.